In this video, I'm going to show you how to check your work whenever you're doing implicit differentiation with Mathematica or with Wolfram Alpha. I have here 3 examples. What we're going to do is implicitly differentiate each one with respect to x. Each of these examples I've tried to write just using basic math notation, but I'm going to show you how to convert it into the right language and use the right commands in order to get y prime of x implicitly. Okay, for this first one, we're looking at the xy points that define the unit circle in the xy plane. What we're going to do is differentiate this equation with respect to x. You don't have to use implicit differentiation here, but if you want to, can make the computation nicer. What we want to say is imagine that y is a function of x. So whenever I do implicit differentiation, when I set up my y variable, I'm going to put it into Mathematica, denoting it as a function of x. We need to use a double equal sign here instead of a single one. That's a common mistake to make in this context. Then what we're going to say, now that we're all ready, is we want to differentiate this. So capital D square bracket, then it's the equation where y is a function of x and we're using 2 equal symbols. We want to differentiate with respect to x, and that's it for the initial round of differentiation. So let me do shift return. Now, if you compare this to implicitly differentiating this equation by hand, it should look exactly like what you would do by hand. So we have 2x as the derivative of x squared, and then using the chain rule to differentiate y squared, where y is a function of x, that turns into 2y prime. And then, of course, the derivative of the constant 1 is just 0. However, often with implicit differentiation, you want to solve for y prime. So let's use the solve command. In order to plug in what we just computed the line above, I will use the percentage symbol. And then we want to solve for y prime of x. Again, that should be exactly what you get if you take this equation and actually try to isolate y prime. You subtract 2x over, divide by 2y, the 2's cancel out, and you get x over y. Let me show you a couple modifications that you can make at this stage. If you want to go from y of x back to y, you can do slash dot y goes to, y of x rather, goes to y, like that. So that will replace the expression y of x, which is plain old y. And then if it helps you read it, you can also do slash slash traditional form. So differentiating x squared plus y squared equals 1 implicitly gives us that y prime is negative x over y. Let's do example 2. It's going to be all the same steps. We have here the equation x squared plus y squared, that quantity squared, equals 6x squared plus y squared. The graph of this curve is actually something called a hippoed. It's kind of a neat shape in the xy plane. All right, same steps as before. Everywhere I have y, I'm going to tell Mathematica that y needs to be treated as a function of x. So we have y of x. The single equals needs to be 2 equal symbols. Then we are going to differentiate this expression with respect to x. Now looking at this, if you were working through this as a calculus problem, this should reflect the work that you would do if you differentiated the line above. So the left-hand side, if you leave that squared, you don't expand it, then using the power rule with the chain rule, we get 2 times x squared plus y squared, that's here. And then differentiate the inside, it's going to be 2x plus 2y prime. So this left-hand side is exactly the derivative of the original left-hand side with respect to x. And then looking over at the right-hand side, we have 12x plus 2y prime. Now I would expect a calculus student to isolate y prime by hand on paper, and then you can check yourself by saying, hey, let's solve this for y prime of x. We get this expression, which is a little harder to read than the line above, but what we can do is say, let's take with slash dot y of x and replace it with y. And then let's also write this in traditional form. So there's our derivative dy dx fully solved for and in a way which is nice to read. If you are working in Mathematica, go ahead and try example 3 on your own. Pause this video and then come back and see how I solve the problem. All right, the first thing I'm going to do is take y and indicate that it's a function of x, make sure my equal symbol is doubled, and then we are ready to differentiate this expression with respect to x. Once again, if you do this by hand, pencil on paper, what you write down should look exactly like this. Let's now solve this expression for the derivative dy dx, or y prime of x. And as we do that, I'm going to go ahead and say that y of x needs to be replaced with y, and let's print this out in traditional form. All right, so that's our derivative dy dx. Let me show you how you can do this in Wolfram Alpha. So here I've opened up wolframalpha.com and I've put the equation that we were just looking at. It's going to look like all the same steps. So I'm going to take y and replace it with y of x, drop in an extra equal symbol. We want to differentiate this now with respect to x. I hit enter to run this. And what you'll notice is that Wolfram Alpha actually solves it for us. So this is the same form for dy dx that we arrived at when we got to the end of our computation in Mathematica. I hope you enjoyed this demonstration of implicit differentiation. Thank you for your attention.